Picture Earth 4.5 billion years ago. There are no oceans, no lakes, no rivers, just molten rock spinning through the darkness of space, glowing like an ember fresh from a cosmic forge. The planet we call home exists only as a ball of liquid stone, its surface temperature hot enough to vaporize lead instantly. But the universe has a surprise waiting. High above this hellish world, a delivery system operates on a scale that defies imagination. Comets and asteroids hurtle through space like celestial cargo ships, each one carrying something precious locked in ice, water. Every impact brings more of this essential ingredient, though it seems impossible that anything so delicate could survive the violence of planetary formation. Here's what's actually happening during these collisions. When a comet slams into the molten surface, the water doesn't simply boil away. Some of it becomes trapped in the rocks themselves, while vast quantities shoot into the atmosphere as superheated steam. For millions of years, Earth develops a thick blanket of water vapor that wraps around the planet like a cosmic pressure cooker. The atmosphere during this time contains so much steam that if you could somehow stand on the surface and look up, you wouldn't see stars or space, just an endless ceiling of churning vapor. The atmospheric pressure builds to levels 20 times greater than what we experience today. This crushing weight of steam creates the perfect conditions for something extraordinary to occur. As the planet slowly cools, a threshold approaches. When surface temperatures finally drop below 100 degrees Celsius, the steam begins to condense. But here's the remarkable part. The first raindrops don't make it to the ground. They fall partway through the atmosphere before the heat rising from below turns them back into vapor. Imagine rain that evaporates before it can touch Earth, creating a cycle of falling and rising water that continues for thousands of years. Eventually, the cooling reaches a tipping point. Surface temperatures drop enough that raindrops survive the entire journey downward. When this happens, the deluge begins. For millions of years, storms rage across the planet with an intensity that makes hurricanes look gentle. The sky opens up and pours continuously, as if all the water vapor that accumulated over geological ages decides to fall at once. These aren't ordinary rainstorms. They represent the largest water transfer in Earth's history, the moment when an ocean's worth of vapor becomes liquid and seeks the lowest places on the planetary surface. The young Earth's crust has already cracked and buckled into vast basins, and these depressions become catching bowls for the endless rain. When we talk about how much water eventually fills these basins, the numbers challenge human comprehension. The oceans that form contain 1.37 billion cubic kilometers of water. To understand this scale, imagine covering the entire United States, from coast to coast, border to border, under 3 kilometers of water. That's the volume we're dealing with. Every lake, every river, every swimming pool on Earth today contains less than 3% of the water that pours into these ancient ocean basins. The ocean becomes Earth's most powerful sculptor almost immediately. Water possesses a quality that makes it uniquely destructive to rock. It finds every crack and crevice, freezes and expands, dissolves minerals grain by grain. Coastlines that took millions of years to form can be reshaped by a single storm. Mountain ranges slowly surrender to rivers that carry their remains to the sea. But water does more than just erode. It connects. Every raindrop that falls begins a journey through the water cycle that links the highest clouds to the deepest ocean trenches. A molecule of water might spend years traveling through groundwater, months drifting in the atmosphere, or centuries locked in glacial ice before returning to the sea. This cycling creates a planetary circulatory system that moves energy, nutrients, and even living organisms across vast distances. Here's where the story takes an unexpected turn. Ancient tidal forces, far stronger than anything we experience today, begin kneading the young planet like cosmic hands working dough. The Moon orbits much closer to Earth during this period, creating tides that rise and fall by hundreds of meters. These massive tidal forces don't just move water, they stretch and compress the planet itself. The solid Earth flexes under these gravitational pulls like a rubber ball being squeezed rhythmically. This flexing generates heat through friction, keeping the planet's interior molten and driving geological processes that shape the surface. Volcanic activity increases during high tides, while the constant stretching and relaxing of the crust creates fracture patterns that will influence the locations of continents and ocean basins for billions of years to come. As seawater fills the growing ocean basins, something remarkable happens to its chemistry. The water begins dissolving minerals from the rocks it touches: sodium, chlorine, magnesium, sulfur, calcium. These dissolved substances transform ordinary H2O into a complex chemical soup. We think of seawater as simply salty, but it actually contains traces of nearly every element found on Earth. This mineral-rich water creates conditions unlike anything that existed before. The ocean becomes a vast chemical laboratory where different substances can interact in countless combinations. Some dissolved minerals make the water denser, causing it to sink. Others react with each other to form new compounds. Temperature differences create circulation patterns that mix these chemicals throughout the growing ocean basins. The early ocean also develops layers with different properties. Surface water, heated by the young sun, becomes less dense and floats above cooler, saltier water below. These density differences drive the first ocean currents, slow, massive rivers of water that begin redistributing heat around the planet. Even before life appears, the ocean starts influencing global climate by moving warm water toward the poles and cold water toward the equator. Volcanic activity beneath the ocean adds another dimension to this chemical complexity. Underwater volcanoes and hydrothermal vents pump heated water and dissolved metals into the sea. These underwater hot springs create localized environments where water temperatures can exceed the normal boiling point, yet remain liquid due to the crushing pressure of the deep ocean. The combination of dissolved minerals, temperature gradients, and chemical energy from volcanic activity transforms the ocean into something unprecedented in the solar system, a planetary-scale chemical reactor capable of supporting complex reactions. Unknown to the young Earth, these conditions are preparing the stage for the most remarkable development in the planet's history. The ocean's role as a sculptor continues to intensify as the water cycle becomes more established. Rivers carve channels through continents, carrying sediments that will become the raw materials for future rock layers. Coastal erosion creates bays and headlands. The freeze-thaw cycle of water in cracks breaks apart mountain ranges grain by grain. But perhaps most importantly, the ocean begins establishing the patterns that will govern Earth's climate for billions of years. Large bodies of water store enormous amounts of heat, energy, and release it slowly, moderating temperature extremes. Ocean currents start redistributing this heat energy around the globe, creating the first climate zones. Areas near large bodies of water develop milder temperatures than inland regions. The young ocean also begins its long career as Earth's primary weather engine. Water evaporating from the surface creates clouds that shade the planet and redistribute fresh water through precipitation. Storm systems begin forming over warm ocean areas and carrying energy toward land. The ocean's thermal mass starts buffering the planet against rapid temperature changes that could make conditions too extreme for what's coming next. As this first chapter in Earth's ocean story concludes, our planet has transformed from a ball of molten rock into a world where vast bodies of liquid water dominate the surface. The ocean basins hold more water than will ever exist again in Earth's history. 2p4. Some will eventually become locked in ice or bound up in living organisms, but never again will the planet be quite this wet. The stage is now set for the most extraordinary development in Earth's history. In the depths of these ancient oceans, where crushing pressure and mineral-rich water create conditions found nowhere else in the solar system, The first sparks of life are about to ignite. The ocean has become more than just a body of water. It's a planetary system capable of supporting complexity beyond imagination. The water that shaped this world will soon nurture phenomena that will transform not just the ocean, but the entire planet. Chemistry is about to become biology, and the ocean's next chapter will be its most remarkable yet. 2 miles beneath the ocean's surface, where no sunlight has ever penetrated, and the weight of water above presses down with the force of 350 cars stacked overhead, something extraordinary is about to happen. In this crushing darkness, volcanic vents crack open the seafloor like wounds in the Earth's skin, releasing superheated water into the abyss. The temperatures here challenge everything we think we know about the limits of existence. Water shoots from these underwater geysers at 400 degrees Celsius, hot enough to instantly melt lead, hot enough to kill any surface life form in milliseconds. Yet somehow, impossibly, this hellish environment becomes the birthplace of all life on Earth. Here's what's actually happening in these deep-sea furnaces. The water doesn't boil despite its extreme temperature, because the crushing pressure of 2 miles of ocean keeps it in liquid form. This creates conditions that exist nowhere else in the solar system. Liquid water far hotter than anything found on the surface, enriched with minerals dissolved from the Earth's interior. The chemistry unfolding around these vents reads like a recipe for impossibility. Hydrogen sulfide, iron, copper, zinc, and dozens of other elements pour into the water, creating a toxic soup that would be instantly lethal to any complex life form. But in this primordial laboratory, simple molecules begin an intricate dance that will change everything. Picture molecules as cosmic Lego blocks, constantly bumping into each other in the mineral-rich water. Most collisions result in nothing. The molecules bounce apart and continue their random motion. But occasionally, under just the right conditions of temperature, pressure, and chemistry, something clicks into place. 2 molecules stick together, then 3, then more. The universe has been experimenting with molecular combinations for billions of years, but something different happens in these deep-sea vents. The energy from the heated water and the specific mix of chemicals create conditions where molecules don't just combine, they begin copying themselves. This is the moment when chemistry becomes biology, when matter first discovers the secret of reproduction. These first living things exist as nothing more than self-replicating chemical reactions. They have no cells, no DNA as we understand it, no recognizable structure. They're simply chemical processes that have learned to perpetuate themselves, feeding on the energy flowing from Earth's interior. But this simple trick, the ability to make copies of themselves, represents the most significant development in the planet's 4.5 billion year history. Evolution begins immediately, though not as the gradual process we often imagine. In the extreme environment of the deep-sea vents, change happens rapidly. Chemical reactions that can copy themselves more efficiently quickly outnumber those that can't. Variations that can survive, slight changes in temperature or chemistry persist while others disappear. Within relatively short geological time periods, these chemical systems become more complex and more stable. The first breakthrough comes when some of these chemical systems develop the ability to create protective boundaries around themselves. These primitive membranes don't just separate inside from outside, they create the first true individuals, distinct entities that can maintain their own internal chemistry while interacting with their environment. The age of cellular life begins. But here's where the story takes an unexpected turn. While surface dwellers like us depend entirely on energy from the sun, these deep-sea pioneers discover something remarkable. They can harvest energy directly from chemicals. They learn to break apart hydrogen sulfide and extract energy from iron and sulfur compounds. This process, called chemosynthesis, creates Earth's first independent ecosystems, communities of life that could thrive even if the sun went dark. As these early organisms multiply and diversify around hydrothermal vents, Some begin venturing upward into the ocean's middle depths. They enter a realm of eternal twilight, where the last traces of sunlight fade into perpetual darkness. The water here is cold, the pressure immense, but there's no crushing heat or toxic chemistry to contend with. In this vast middle ocean, evolution experiments with one of its most spectacular innovations, bioluminescence. Organisms begin manufacturing their own light through chemical reactions, turning the deep ocean into a living constellation. Unlike the fire we create by burning fuel, bioluminescence produces light without heat, achieving near-perfect efficiency that human technology still struggles to match. The variety of these living lights defies imagination. Some organisms create steady glows, others produce flashing patterns. Some use bioluminescence to attract prey, luring smaller creatures toward their mouths like underwater anglerfish. Others employ it for communication, sending signals across the darkness to potential mates or rivals. Still others use it as a defense mechanism, creating sudden bursts of light to confuse predators. The deep ocean becomes a three-dimensional universe of living light, with creatures communicating through bioluminescent displays across vast distances. Jellyfish pulse with ethereal blue glows. Deep-sea fish sport rows of lights along their sides like underwater cities. Microscopic organisms create trails of sparkles when disturbed, turning the movement of larger creatures into blazing comets streaking through the abyss. As life spreads throughout the ocean depths, some organisms begin another extraordinary journey toward the surface. This migration upward requires solving entirely new challenges. Surface waters offer abundant sunlight but also temperature variations, storms, and eventually, the deadly radiation of unfiltered solar energy. The organisms that successfully colonize surface waters develop the ability to harness sunlight directly through photosynthesis. This innovation dwarfs even the development of life itself in terms of its planetary impact. For the first time, organisms can capture energy directly from the sun and use it to build complex molecules from simple ingredients like carbon dioxide and water. Photosynthesis transforms not just life, but the entire planet. As countless microscopic organisms begin producing oxygen as a waste product, the ocean's chemistry changes dramatically. Oxygen, which had been virtually absent from Earth's atmosphere and oceans, begins accumulating to levels that would have been toxic to the original deep-sea life forms. This oxygen revolution triggers the first mass extinction, as many early life forms, adapted to an oxygen-free world, cannot survive in the increasingly oxygen-rich environment. But it also opens up entirely new possibilities for life. Oxygen enables much more efficient energy production, allowing organisms to grow larger and more complex than ever before. The stage is set for evolution's next spectacular experiment, HAC, multicellular life. Individual cells begin cooperating, specializing in different functions while remaining part of larger organisms. Some cells focus on movement, others on sensing the environment, still others on reproduction. This division of labor allows life forms to achieve sizes and capabilities impossible for single cells. In the ocean depths, creatures begin growing to proportions that challenge the imagination. The blue whale, Earth's largest animal, develops a heart the size of a small car, so large that its arteries could accommodate a human crawling through them. When a blue whale calls, its voice travels thousands of kilometers through ocean basins, creating a communication network that spans entire ocean regions. These giants of the deep ocean represent the ultimate expression of life's potential when freed from the constraints of land. In water, organisms can grow to sizes impossible on land because the water itself provides structural support. Blue whales can reach lengths of 30 meters and weights of 200 tons, yet move through their environment with grace that belies their enormous size. The songs of these ocean giants create one of the planet's most remarkable phenomena. Blue whale calls register at frequencies so low that humans can't hear them without special equipment. These infrasonic calls travel through the ocean's sound channel, a layer of water where temperature and pressure conditions allow sound to propagate across vast distances with minimal energy loss. A blue whale calling off the coast of California can potentially be heard by another blue whale near Hawaii, thousands of kilometers away. This creates a communication network of unprecedented scale, allowing these magnificent creatures to maintain contact across entire ocean basins. During migration seasons, the ocean fills with a symphony of whale songs, a planetary-scale conversation conducted in frequencies below human hearing. But the ocean's story of life includes more than just giants. Mass extinctions periodically reset evolution's experiments, wiping out dominant life forms and creating opportunities for new innovations. The end Permian extinction eliminates 96% of marine species, while the asteroid impact that ends the age of dinosaurs dramatically alters ocean ecosystems. Yet each extinction event demonstrates life's remarkable resilience. Survivors quickly diversify to fill empty ecological niches, often developing entirely new body plans and survival strategies. The extinction that eliminates marine reptiles allows whales to colonize ocean environments, while the disappearance of certain predators enables new prey species to flourish. Through all these changes, the deep-sea vents where life first emerged continue operating as they have for billions of years. These underwater oases still support unique ecosystems based on chemosynthesis, maintaining a direct connection to the earliest chapters of life's story. Tube worms grow to lengths of 2 meters around these vents, supported entirely by bacteria that harvest energy from the vent chemicals. The discovery of these modern hydrothermal vent communities revolutionized our understanding of life's possibilities. If complex ecosystems can thrive in the crushing depths around underwater volcanoes, life might exist in environments we previously considered impossible, perhaps in the subsurface oceans of distant moons, or in the deep groundwater of other planets. As this chapter of the ocean story concludes, life has transformed from simple chemical reactions around deep-sea vents into a magnificent array of creatures that inhabit every layer of the ocean. From the crushing depths where giant tube worms cluster around volcanic vents, to the sunlit surface where microscopic organisms produce most of Earth's oxygen, the ocean has become life's greatest laboratory. The chemical soup that once filled Earth's early ocean basins now pulses with billions of organisms, each adapted to specific conditions of temperature, pressure, and chemistry. These life forms don't just inhabit the ocean, they actively shape it, influencing everything from water chemistry to the movement of currents. The next chapter of this story will reveal how these countless organisms, from microscopic plankton to massive whales, create moving rivers within the ocean itself, currents that dwarf any river on land and connect every corner of our blue planet. Beneath the waves lies a secret that would astonish even the most experienced sailor looking down at calm seas. What appears to be a static body of water is actually flowing, not just in surface waves driven by wind, but in massive rivers that dwarf every waterway on land combined. These hidden currents move water, heat, nutrients, and life itself across distances that span continents. The Gulf Stream alone carries a volume of water that challenges human comprehension. Picture the Amazon River, Earth's mightiest waterway, carrying 6 million cubic meters of water past any given point each second. Now imagine a current moving 150 times that volume, 900 million cubic meters per second. That's the Gulf Stream, a river within the ocean that flows northward along North America's eastern coast with the power of thousands of Amazon rivers combined. Here's what's actually happening beneath the surface. The Gulf Stream moves like a liquid highway, carrying warm tropical water from the Caribbean toward the North Atlantic at speeds reaching 9 kilometers per hour. This current is so distinct from surrounding water that sailors can literally see where it begins and ends. The warm Gulf Stream water appears deep blue, while the cooler water on either side looks green or grey. The energy contained in this flowing water exceeds the output of thousands of power plants. If we could somehow harness just 1% of the Gulf Stream's kinetic energy, it would supply electricity for millions of homes. Yet this represents only one current in a global network of underwater rivers that operate continuously, driven by forces more powerful and persistent than any human technology. These ocean currents follow invisible highways carved by three fundamental forces: Earth's rotation, temperature differences, and variations in salt content. The Coriolis effect, caused by our planet's rotation, deflects moving water in predictable patterns. In the northern hemisphere, currents curve to the right. In the southern hemisphere, they curve to the left. This creates the circular patterns we see in ocean basins, massive gyres that can take decades to complete a single rotation. Temperature differences provide the engine that drives these currents. When the sun heats tropical waters, that warm water becomes less dense and tends to flow toward cooler regions. Meanwhile, cold water from polar regions sinks and flows along the ocean floor toward the equator. This creates a global conveyor belt of moving water that redistributes heat around the planet more efficiently than any human-designed system. Salt content adds another layer of complexity to this underwater choreography. When seawater evaporates, it leaves salt behind, making the remaining water denser and more likely to sink. When fresh water from melting ice or river runoff mixes with seawater, it reduces salinity and creates water that tends to float. These density differences drive vertical movements that connect surface currents to deep-sea flows. In the deep ocean, something even more spectacular occurs: underwater waterfalls that dwarf any cascade found on land. The Denmark Strait Cataract, flowing between Greenland and Iceland, plunges 3.5 kilometers down the underwater landscape with a flow rate 11 times greater than Niagara Falls. This underwater waterfall carries cold, dense water from the shallow seas around Greenland into the deep Atlantic basin. Unlike surface waterfalls driven by gravity alone, these underwater cascades result from the complex interplay of temperature, salinity, and pressure. Cold Arctic water, made denser by its low temperature and high salt content, literally flows underneath warmer Atlantic water like an invisible river pouring over an underwater cliff. These deep water flows begin journeys that can last 1,000 years. Water sinking in the North Atlantic carries oxygen and nutrients into the deep ocean basins, then flows southward along the ocean floor. This deep current travels around Africa, into the Indian Ocean, across to the Pacific, and eventually returns to the surface in other parts of the world through a process called upwelling. Imagine a single molecule of water beginning this journey. It starts at the surface near Greenland, absorbs oxygen from the atmosphere, then sinks into the depths when winter cooling makes it dense enough to descend. For the next several centuries, this molecule travels through the deep ocean, carrying its payload of oxygen to creatures living in the abyss thousands of kilometers from where it first entered the depths. This global circulation system, known as the thermohaline circulation, acts as the planet's primary heat distribution network. Without these currents, tropical regions would be much hotter and polar regions much colder than they are today. Europe's surprisingly mild climate, despite its northern latitude, results directly from warm water carried by the Gulf Stream from tropical regions. The biological implications of these currents extend far beyond simple heat transport. Microscopic plankton, both plant and animal varieties, ride these underwater highways like passengers on a planetary transportation system. These tiny organisms form the foundation of ocean food webs, yet many cannot swim strongly enough to control their horizontal movement. Ocean currents become their primary means of transportation and dispersal. Phytoplankton, the microscopic plants that drift in surface waters, produce approximately 70% of Earth's oxygen through photosynthesis. These organisms, individually too small to see without a microscope, collectively outweigh all terrestrial plants combined. Ocean currents distribute these vital oxygen producers throughout the world's seas, ensuring that photosynthesis occurs across vast areas of the planet's surface. The seasonal movements of these currents trigger some of the most spectacular migrations in the natural world. As currents shift with changing temperatures and wind patterns, they create temporary highways that billions of creatures follow across entire ocean basins. Nutrients brought up from deep waters by seasonal currents create feeding opportunities that support massive populations of marine life. During spring in polar regions, melting ice changes the salinity and temperature of surface waters, altering current patterns and bringing nutrient-rich deep water toward the surface. This upwelling of nutrients triggers explosive blooms of phytoplankton, which in turn support zooplankton, small fish, and eventually the largest creatures in the ocean. Blue whales time their migrations to coincide with these seasonal current changes, following underwater highways that lead to areas where currents create ideal feeding conditions. A blue whale might travel 25,000 kilometers during a single migration, using current patterns that have remained consistent for thousands of years to navigate between feeding and breeding areas. The precision of these migrations amazes scientists studying animal navigation. Creatures ranging from tiny zooplankton to massive whales somehow sense the subtle changes in water temperature, chemistry, and movement that signal the presence of favorable currents. Some species can detect current boundaries that exist only a few meters wide, threading their way along underwater highways invisible to human senses. Ocean currents also create physical structures within the sea that concentrate marine life. When currents converge, they create downwelling zones where surface water sinks, often carrying floating debris and organisms to greater depths. When currents diverge, they create upwelling zones where deep water rises to the surface, bringing nutrients that support abundant marine life. These current-driven upwelling zones support some of the world's most productive fisheries. Off the coasts of Peru, California, and West Africa, deep currents bring cold, nutrient-rich water to the surface, creating conditions that support enormous populations of fish. These regions, covering less than 1% of the ocean's surface area, produce approximately 20% of the world's fish catch. Long before satellites could track ocean currents or submarines could reach the deepest trenches, humans looked out at endless waters and felt an irresistible pull toward the unknown. The ocean called to something deep in the human spirit, a need to discover what lay beyond the horizon, beneath the waves, in the vast blue spaces that covered most of our planet. The first master navigators emerged in the Pacific, where Polynesian sailors developed skills that bordered on the supernatural. These ocean voyagers learned to read the sea itself like a vast living map. They could detect islands beyond the horizon by watching how waves reflected off distant land masses, creating subtle interference patterns that trained eyes could recognize from dozens of kilometers away. Here's what's actually happening when a Polynesian navigator reads the waves. As ocean swells approach an island, they bounce off the underwater slopes and coastal features, creating complex patterns of crossing waves. These reflected swells interact with incoming waves to create zones of rougher or calmer water that extend far beyond the visual horizon. A skilled navigator could feel these patterns through the hull of an outrigger canoe and determine not just the presence of land, but its approximate size and distance. These navigators also mastered the art of reading clouds for clues about hidden islands. Clouds tend to form differently over land than over open water, creating distinctive patterns that could reveal the presence of an island a full day's sail away. The undersides of clouds over lagoons often reflected the turquoise color of shallow water, while clouds over dense vegetation appeared greener than those over open ocean. Star navigation in the Pacific required memorizing the movements of hundreds of celestial objects across thousands of possible routes. Polynesian navigators learned to use rising and setting points of stars as compass bearings, following sequences of guide stars that would lead them across vast ocean distances. They understood that different stars served as guides at different times of year and could navigate equally well regardless of season. The precision of these ancient navigators challenges modern understanding. Using only outrigger canoes, they successfully settled islands scattered across 1/3 of Earth's surface, traveling distances of thousands of kilometers with accuracy that rivals modern GPS navigation. The settlement of Easter Island required a journey of over 3,700 kilometers from the nearest inhabited land, a voyage into complete unknown, accomplished without instruments, charts, or any certainty that land existed at their destination. But Polynesian navigators didn't just reach distant islands, they established regular trading routes that connected island cultures across the Pacific. Archaeological evidence shows that tools made from volcanic glass in one island group appear in settlements thousands of kilometers away, indicating systematic voyaging and trade networks that operated for centuries. These ocean masters also learned to read biological signs with remarkable sophistication. Certain seabirds forage during the day and return to land-based roosts at night, so observing their flight patterns at dawn and dusk could indicate the direction and approximate distance to nearest land. Different species had different ranging distances, providing navigators with rough estimates of how far they were from shore. The skills of these Pacific navigators were so advanced that when European explorers finally reached Polynesian islands, they initially refused to believe that such sophisticated navigation was possible without instruments. Captain James Cook, one of history's greatest navigators himself, expressed amazement at the abilities of Polynesian pilots who could guide his ships through dangerous reef passages with precision that exceeded his own charts. Cook's own contributions to ocean exploration were revolutionary in different ways. His 3 Pacific voyages, between 1768 and 1779, systematically mapped vast areas of the ocean for the first time, using chronometers and celestial navigation to establish precise longitude measurements. Cook proved that accurate ocean navigation was possible using scientific instruments, opening the seas to systematic exploration. During Cook's voyages, naturalist Joseph Banks collected the first scientific specimens from Pacific ecosystems, beginning the formal study of marine biodiversity. Banks observed that different ocean regions supported entirely different assemblages of species, suggesting that the ocean contained multiple distinct biological provinces rather than being a uniform environment. Charles Darwin's voyage aboard the HMS Beagle added another crucial dimension to ocean exploration. While developing his theory of evolution, Darwin made detailed observations of coral atolls that revealed something extraordinary about ocean geology. He realized that ring-shaped coral reefs marked the locations of volcanic islands that had slowly sunk into the sea over geological time periods. Darwin's coral atoll theory explained how living reefs could exist in water far too deep for coral polyps to survive. As volcanic islands gradually subsided due to their own weight and geological processes, coral reefs growing around their shores continued building upward, maintaining their position near the surface, while the original land disappeared beneath the waves. This insight revealed that the ocean floor was far more dynamic than anyone had imagined. The 1870s marked a watershed moment in ocean exploration with the HMS Challenger Expedition HMS, the first systematic scientific investigation of the deep sea. This 3.5-year voyage circumnavigated the globe while conducting depth soundings, water sampling, and biological collection that revealed the ocean's true 3-dimensional complexity. The Challenger's crew discovered that the ocean contained layers with distinctly different temperatures, salinities, and biological communities. They hauled up creatures from the abyss that looked so alien that many scientists initially doubted they could be real. Glass sponges with skeletons like spun crystal, deep-sea fish with massive mouths, and bioluminescent lures, and creatures that seemed to challenge every assumption about the requirements for life. One of the Challenger expedition's most shocking discoveries was the sheer depth of the ocean. Previous estimates had suggested that the deepest parts of the sea might reach a few thousand meters, but Challenger's soundings revealed trenches extending to depths exceeding 8,000 meters. The ocean was far deeper and more voluminous than anyone had dreamed. The expedition also discovered the global extent of ocean currents by measuring temperature and salinity changes at different depths across ocean basins. These measurements revealed that the deep ocean was filled with moving water masses that originated in polar regions and flowed along the bottom toward the equator. The ocean was not a static body of water, but a dynamic system in constant motion. As technology advanced, explorers began venturing beneath the ocean surface itself. William Beebe's bathysphere dives in the 1930s brought the first human observers into the deep-sea environment. Lowered on a steel cable to depths of over 900 meters, Beebe became the first person to witness bioluminescent displays in their natural habitat. Beebe's descriptions of the deep ocean read like accounts from an alien world. He observed creatures that produced their own light in colors ranging from deep blue to brilliant red, creating displays that pulsed and flickered in the eternal darkness. Some fish carried rows of lights along their sides like underwater cities, while others sported lures that glowed like neon signs in the abyss. The bathysphere dives also revealed the incredible clarity of deep ocean water. Without suspended particles or plankton to scatter light, the beam from Beebe's searchlight could penetrate much farther than expected, revealing a crystal-clear environment where bioluminescent displays stood out with startling intensity. Jacques Cousteau revolutionized underwater exploration by developing the aqualung, which freed divers from surface-supplied air and allowed them to move freely through underwater environments. Cousteau's films brought the underwater world to millions of people for the first time, revealing coral gardens, shark encounters, and marine behavior that had been hidden from human observation. Cousteau's expeditions demonstrated that the ocean contained ecosystems as complex and beautiful as any terrestrial environment. His footage of coral reefs showed underwater forests where fish moved like flocks of birds through branching coral structures. His encounters with large marine animals revealed behaviors and intelligence that challenged assumptions about marine life. The development of deep-sea submersibles pushed human exploration to even greater depths. The bathyscaphe Trieste reached the deepest known point in the ocean, Challenger Deep in the Mariana Trench, in 1960. At a depth of nearly 11 kilometers, where pressure exceeds 1,000 atmospheres, Jacques Piccard and Don Walsh became the first humans to reach the ocean's ultimate frontier. The Trieste descent revealed that life existed even in the ocean's deepest places. At maximum depth, the explorers observed flatfish and other creatures living on the seafloor under crushing pressure that would instantly destroy any surface organism. This discovery proved that life could adapt to conditions far more extreme than anyone had thought possible. The view from the Challenger Deep also provided perspective on the ocean's true scale. The deepest ocean trenches reached depths that dwarf terrestrial mountain ranges. If Mount Everest were placed in the Mariana Trench, its peak would still be covered by over 2 kilometers of water. The ocean's vertical dimension exceeded the height of Earth's tallest mountains. Modern deep-sea exploration has revealed that the ocean contains geological features that rival anything found on land. Underwater mountain ranges snake around the planet like seams on a baseball, rising from abyssal plains to heights that rival the Alps or Rockies. Underwater canyons cut into continental margins create gorges deeper and wider than the Grand Canyon. The discovery of hydrothermal vents in 1977 represented perhaps the most significant breakthrough in ocean exploration since the Challenger expedition. These underwater oases, supporting complex ecosystems based on chemical energy rather than sunlight, proved that life could thrive in environments previously thought impossible for complex organisms. The vent communities revealed entirely new forms of life, including giant tube worms that reach lengths of 2 meters and have no digestive systems, instead harboring symbiotic bacteria that convert chemicals into food. These discoveries suggested that life might exist in similar environments throughout the solar system, wherever liquid water and chemical energy sources coexisted. Robotic exploration has extended human reach into ocean environments too dangerous or remote for manned submersibles. Remotely operated vehicles can spend months in the deep ocean, mapping seafloor features and observing marine life without the safety constraints that limit human diving operations. These robotic explorers have discovered underwater lakes and rivers, where dense, salty water flows along the seafloor beneath normal seawater. They've found underwater waterfalls where cold water cascades off continental shelves into abyssal depths. They've documented migration routes of deep-sea creatures and revealed the true extent of bioluminescent communication in the ocean's depths. As this chapter of exploration concludes, humans have progressed from reading wave patterns in outrigger canoes to operating robot submarines in the deepest ocean trenches. Each generation of explorers has revealed new layers of complexity in the ocean system, from the surface currents that Polynesian navigators learned to read, to the deep-sea ecosystems that modern submersibles continue to discover. The brave individuals who dared to venture into the ocean's mysteries have transformed our understanding of our planet. They've shown us that the sea contains not just water, but entire worlds of life and geological activity that operate according to principles we're still learning to understand. The next chapter will explore how modern technology has opened new windows into these underwater worlds, providing tools that allow us to observe ocean processes with precision that earlier explorers could never have imagined. The Gulf Stream creates another type of biological concentration through its boundary effects. The edge of this current acts like a fence in the ocean, creating different conditions on either side. Many marine species congregate along these current boundaries, taking advantage of the mixing and upwelling that occurs where different water masses meet. Modern technology has revealed the true complexity of these underwater river systems. Satellite measurements show that ocean currents contain eddies, meanders, and turbulent features similar to atmospheric weather systems. Some of these oceanic storms can persist for months, transporting water and marine life far from their typical ranges. The interaction between surface currents and underwater topography creates additional complexity. When the Gulf Stream encounters underwater mountains or the continental slope, it can split into multiple streams, create temporary eddies, or change direction entirely. These interactions make ocean currents far more dynamic and unpredictable than early oceanographers imagined. Ring currents, 200 massive circular flows that break off from major currents, can transport tropical water hundreds of kilometers into temperate regions or carry cold water far from its source. These rings act like oceanic delivery systems, moving not just water, but entire ecosystems from one region to another. Climate patterns across the globe depend critically on the stability of these ocean current systems. The Atlantic meridional overturning circulation, which includes the Gulf Stream, has slowed by approximately 15% since the mid-20th century, possibly due to freshwater input from melting Arctic ice. Even small changes in this circulation pattern could dramatically alter weather patterns across Europe and North America. The El Niño phenomenon demonstrates how changes in Pacific Ocean currents can affect weather worldwide. During El Niño years, alterations in current patterns shift the locations of upwelling zones, change atmospheric circulation patterns, and create weather anomalies that span the globe. Droughts in Australia, floods in California, and altered hurricane patterns in the Atlantic can all trace their origins to changes in Pacific Ocean currents. As this chapter of the ocean story concludes, we see that the seas contain not just water, but a dynamic system of flowing rivers that connect every corner of our planet. These currents transport heat from the tropics to the poles, carry nutrients from deep waters to surface ecosystems, and provide highways for the greatest migrations in the natural world. The hidden rivers flowing beneath the waves operate on scales that dwarf human experience, yet their influence reaches into every aspect of life on Earth. They control our climate, support our fisheries, and maintain the delicate balance of chemical and biological processes that make our planet habitable. In the next chapter, we'll follow the brave individuals who first dared to explore these mysterious currents and the creatures they support, beginning humanity's long journey to understand the ocean's secrets. Long before satellites could track ocean currents or submarines could reach the deepest trenches, humans looked out at endless waters and felt an irresistible pull toward the unknown. The ocean called to something deep in the human spirit, a need to discover what lay beyond the horizon, beneath the waves, in the vast blue spaces that covered most of our planet. The first master navigators emerged in the Pacific, where Polynesian sailors developed skills that bordered on the supernatural. These ocean voyagers learned to read the sea itself like a vast, living map. They could detect islands beyond the horizon by watching how waves reflected off distant land masses, creating subtle interference patterns that trained eyes could recognize from dozens of kilometers away. Here's what's actually happening when a Polynesian navigator reads the waves. As ocean swells approach an island, they bounce off the underwater slopes and coastal features, creating complex patterns of crossing waves. These reflected swells interact with incoming waves to create zones of rougher or calmer water that extend far beyond the visual horizon. A skilled navigator could feel these patterns through the hull of an outrigger canoe and determine not just the presence of land, but its approximate size and distance. These navigators also mastered the art of reading clouds for clues about hidden islands. Clouds tend to form differently over land than over open water, creating distinctive patterns that could reveal the presence of an island a full day's sail away. The undersides of clouds over lagoons often reflected the turquoise color of shallow water, while clouds over dense vegetation appeared greener than those over open ocean. Star navigation in the Pacific required memorizing the movements of hundreds of celestial objects across thousands of possible routes. Polynesian navigators learned to use rising and setting points of stars as compass bearings, following sequences of guide stars that would lead them across vast ocean distances. They understood that different stars served as guides at different times of year and could navigate equally well regardless of season. The precision of these ancient navigators challenges modern understanding. Using only outrigger canoes, they successfully settled islands scattered across 1/3 of Earth's surface, traveling distances of thousands of kilometers with accuracy that rivals modern GPS navigation. The settlement of Easter Island required a journey of over 3,700 kilometers from the nearest inhabited land, a voyage into complete unknown, accomplished without instruments, charts, or any certainty that land existed at their destination. But Polynesian navigators didn't just reach distant islands. They established regular trading routes that connected island cultures across the Pacific. Archaeological evidence shows that tools made from volcanic glass in one island group appear in settlements thousands of kilometers away, indicating systematic voyaging and trade networks that operated for centuries. These ocean masters also learned to read biological signs with remarkable sophistication. Certain seabirds forage during the day and return to land-based roosts at night, so observing their flight patterns at dawn and dusk could indicate the direction and approximate distance to nearest land. Different species had different ranging distances, providing navigators with rough estimates of how far they were from shore. The skills of these Pacific navigators were so advanced that when European explorers finally reached Polynesian islands, they initially refused to believe that such sophisticated navigation was possible without instruments. Captain James Cook, one of history's greatest navigators himself, we expressed amazement at the abilities of Polynesian pilots who could guide his ships through dangerous reef passages with precision that exceeded his own charts. Cook's own contributions to ocean exploration were revolutionary in different ways. His 3 Pacific voyages between 1768 and 1779 systematically mapped vast areas of the ocean for the first time. Using chronometers and celestial navigation to establish precise longitude measurements, Cook proved that accurate ocean navigation was possible, using scientific instruments, opening the seas to systematic exploration. During Cook's voyages, naturalist Joseph Banks collected the first scientific specimens from Pacific ecosystems, beginning the formal study of marine biodiversity. Banks observed that different ocean regions supported entirely different assemblages of species, suggesting that the ocean contained multiple distinct biological provinces rather than being a uniform environment. Charles Darwin's voyage aboard the HMS Beagle added another crucial dimension to ocean exploration. While developing his theory of evolution, Darwin made detailed observations of coral atolls that revealed something extraordinary about ocean geology. He realized that ring-shaped coral reefs marked the locations of volcanic islands that had slowly sunk into the sea over geological time periods. Darwin's coral atoll theory explained how living reefs could exist in water far too deep for coral polyps to survive. As volcanic islands gradually subsided due to their own weight and geological processes, coral reefs growing around their shores continued building upward, maintaining their position near the surface, while the original land disappeared beneath the waves. This insight revealed that the ocean floor was far more dynamic than anyone had imagined. The 1870s marked a watershed moment in ocean exploration, with the HMS Challenger expedition, AUCA, the first systematic scientific investigation of the deep sea. This 3.5-year voyage circumnavigated the globe while conducting depth soundings, water sampling, and biological collection that revealed the ocean's true three-dimensional complexity. The Challenger's crew discovered that the ocean contained layers with distinctly different temperatures, salinities, and biological communities. They hauled up creatures from the abyss that looked so alien that many scientists initially doubted they could be real. Glass sponges with skeletons like spun crystal, deep-sea fish with massive mouths and bioluminescent lures, and creatures that seemed to challenge every assumption about the requirements for life. One of the Challenger expedition's most shocking discoveries was the sheer depth of the ocean. Previous estimates had suggested that the deepest parts of the sea might reach a few thousand meters, but Challenger's soundings revealed trenches extending to depths exceeding 8,000 meters. The ocean was far deeper and more voluminous than anyone had dreamed. The expedition also discovered the global extent of ocean currents by measuring temperature and salinity changes at different depths across ocean basins. These measurements revealed that the deep ocean was filled with moving water masses that originated in polar regions and flowed along the bottom toward the equator. The ocean was not a static body of water, but a dynamic system in constant motion. As technology advanced, explorers began venturing beneath the ocean surface itself. William Beebe's bathysphere dives in the 1930s brought the first human observers into the deep-sea environment. Lowered on a steel cable to depths of over 900 meters, Beebe became the first person to witness bioluminescent displays in their natural habitat. Beebe's descriptions of the deep ocean read like accounts from an alien world. He observed creatures that produced their own light in colors ranging from deep blue to brilliant red, creating displays that pulsed and flickered in the eternal darkness. Some fish carried rows of lights along their sides like underwater cities, while others sported lures that glowed like neon signs in the abyss. The bathysphere dives also revealed the incredible clarity of deep ocean water. Without suspended particles or plankton to scatter light, the beam from Beebe's searchlight could penetrate much farther than expected, revealing a crystal-clear environment where bioluminescent displays stood out with startling intensity. Jacques Cousteau revolutionized underwater exploration by developing the aqualung, which freed divers from surface-supplied air and allowed them to move freely through underwater environments. Cousteau's films brought the underwater world to millions of people for the first time, revealing coral gardens, shark encounters, and marine behavior that had been hidden from human observation. Cousteau's expeditions demonstrated that the ocean contained ecosystems as complex and beautiful as any terrestrial environment. His footage of coral reefs showed underwater forests, where fish moved like flocks of birds through branching coral structures. His encounters with large marine animals revealed behaviors and intelligence that challenged assumptions about marine life. the development of deep-sea submersibles pushed human exploration to even greater depths. The bathyscaphe Trieste reached the deepest known point in the ocean, the Challenger Deep in the Mariana Trench, in 1960. At a depth of nearly 11 kilometers, where pressure exceeds 1,000 atmospheres, Jacques Piccard and Don Walsh became the first humans to reach the ocean's ultimate frontier. The Trieste descent revealed that life existed even in the ocean's deepest places. At maximum depth, the explorers observed flatfish and other creatures living on the seafloor under crushing pressure that would instantly destroy any surface organism. This discovery proved that life could adapt to conditions far more extreme than anyone had thought possible. The view from the Challenger Deep also provided perspective on the ocean's true scale. The deepest ocean trenches reached depths that dwarf terrestrial mountain ranges. If Mount Everest were placed in the Mariana Trench, its peak would still be covered by over 2 kilometers of water. The ocean's vertical dimension exceeded the height of Earth's tallest mountains. Modern deep-sea exploration has revealed that the ocean contains geological features that rival anything found on land. Underwater mountain ranges snake around the planet like seams on a baseball, rising from abyssal plains to heights that rival the Alps or Rockies. Underwater canyons cut into continental margins create gorges deeper and wider than the Grand Canyon. The discovery of hydrothermal vents in 1977 represented perhaps the most significant breakthrough in ocean exploration since the Challenger expedition. These underwater oases, supporting complex ecosystems based on chemical energy rather than sunlight, proved that life could thrive in environments previously thought impossible for complex organisms. The vent communities revealed entirely new forms of life, including giant tube worms that reach lengths of 2 meters and have no digestive systems, instead harboring symbiotic bacteria that convert chemicals into food. These discoveries suggested that life might exist in similar environments throughout the solar system, wherever liquid water and chemical energy sources coexisted. Robotic exploration has extended human reach into ocean environments too dangerous or remote for manned submersibles. Remotely operated vehicles can spend months in the deep ocean, mapping seafloor features and observing marine life without the safety constraints that limit human diving operations. These robotic explorers have discovered underwater lakes and rivers, where dense, salty water flows along the seafloor beneath normal seawater. They've found underwater waterfalls where cold water cascades off continental shelves into abyssal depths. They've documented migration routes of deep-sea creatures and revealed the true extent of bioluminescent communication in the ocean's depths. As this chapter of exploration concludes, humans have progressed from reading wave patterns in outrigger canoes to operating robot submarines in the deepest ocean trenches. Each generation of explorers has revealed new layers of complexity in the ocean system, from the surface currents that Polynesian navigators learned to read to the deep-sea ecosystems that modern submersibles continue to discover. The brave individuals who dared to venture into the ocean's mysteries have transformed our understanding of our planet. They've shown us that the sea contains not just water, but entire worlds of life and geological activity that operate according to principles we're still learning to understand. The next chapter will explore how modern technology has opened new windows into these underwater worlds, providing tools that allow us to observe ocean processes with precision that earlier explorers could never have imagined. The Second World War transformed ocean science in ways that no peacetime expedition could have achieved. Military necessity drove rapid development of technologies that would revolutionize our understanding of the hidden underwater world. What began as tools for detecting enemy submarines became windows into ocean realms that had remained invisible since the dawn of human history. Sonar technology, originally developed to hunt German U-boats, began revealing underwater landscapes that dwarfed any mountain range on land. When sound waves traveling at 1,500 meters per second bounced off the seafloor and returned to listening devices, they painted acoustic pictures of a submarine world more dramatic than anything explorers had imagined. Here's what's actually happening when sonar maps the ocean floor. A ship sends out a pulse of sound that spreads downward through the water like an expanding cone. When this sound wave hits the bottom, it reflects back toward the surface, carrying information about the depth, composition, and texture of whatever it encountered. By measuring the time between transmission and return, scientists can calculate precise depths across vast areas of seafloor. The first systematic sonar surveys revealed that the ocean floor contained underwater mountain ranges that snake around the planet like seams on a baseball. The Mid-Atlantic Ridge, running north-south through the Atlantic Ocean, rises from abyssal plains to heights rivaling terrestrial mountain ranges. In some places, these underwater peaks break the surface as islands like Iceland and the Azores. Even more spectacular were the ocean trenches that sonar revealed, underwater chasms so deep they challenged comprehension. The Mariana Trench plunges to depths of nearly 11 kilometers, deeper than Mount Everest is tall. If the world's highest mountain were placed in this trench, its peak would still lie under more than 2 kilometers of water. These discoveries revolutionized understanding of Earth's geology. The ocean floor wasn't a flat, featureless plain as many had assumed, but a landscape of underwater mountains, valleys, plateaus, and canyons that rivaled or exceeded anything found on the continents. The seafloor contained more topographic relief than all the land surfaces combined. Sonar mapping also revealed massive underwater avalanches that reshape entire sections of the ocean floor. Turbidity currents, race-dense mixtures of sediment and water, race down continental slopes at speeds exceeding 100 kilometers per hour, carving submarine canyons and depositing sediment loads that can bury areas the size of small countries. The development of side-scan sonar provided even more detailed views of underwater landscapes. This technology sends sound waves out to the sides of a research vessel, creating detailed images that show individual rocks, biological communities, and human artifacts on the seafloor. Shipwrecks become visible in stunning detail, while previously unknown geological features emerge from the acoustic shadows. Marine archaeology benefited enormously from these sonar advances. Ancient shipwrecks, preserved in the cold, oxygen-poor environment of the deep ocean, began yielding information about historical trade routes, shipbuilding techniques, and past climate conditions. Some wrecks contained cargo that provided the first physical evidence of long-distance trade relationships between ancient civilizations. But sonar revealed more than just seafloor topography. It began detecting something unexpected in the water itself. During the 1940s and 50s, military sonar operators noticed a mysterious layer in the ocean that reflected sound waves almost like a false bottom. This deep scattering layer appeared to move up and down daily, rising toward the surface at night and sinking to greater depths during the day. The deep scattering layer turned out to be one of the most remarkable biological phenomena on Earth, a massive aggregation of marine life that migrates vertically through the ocean every 24 hours. Small fish, squid, jellyfish, and countless other creatures rise toward the surface under cover of darkness to feed, then descend to darker depths during daylight hours to avoid predators. This daily migration involves billions of individual organisms and represents the largest movement of biomass on the planet. The total weight of creatures participating in this vertical migration may exceed the combined weight of all fish caught by human fisheries each year. Yet this enormous biological phenomenon remained completely unknown until sonar technology made it detectable. Satellites revolutionized ocean science by providing the first global view of ocean processes. Unlike ships, which could only observe conditions along their immediate path, satellites could monitor entire ocean basins simultaneously and detect changes occurring over vast areas. This orbital perspective revealed that the ocean was far more dynamic and variable than surface observations had suggested. Satellite measurements of sea surface temperature showed that the ocean contained swirling eddies, meandering currents, and thermal boundaries that shifted constantly. These features, invisible from ships, turned out to control the distribution of marine life and influence weather patterns across entire continents. The precision of satellite temperature measurements amazed scientists accustomed to crude ship-based observations. Orbiting sensors could detect temperature differences as small as 1/10 of a degree Celsius across distances of thousands of kilometers. This revealed that ocean temperature patterns contained intricate details that ship measurements had completely missed. Satellite altimetry added another crucial dimension by measuring the height of the ocean surface with centimeter-level precision. Variations in sea level, caused by currents, temperature differences, and gravitational effects, created a topographic map of the ocean surface that revealed underwater features through their gravitational influence. The combination of satellite data with computer models began revealing connections between ocean processes and global climate that no one had suspected. Changes in Pacific Ocean temperatures could be linked to droughts in Africa, floods in South America, and altered hurricane patterns in the Atlantic. The ocean was not just responding to atmospheric conditions, it was actively driving weather patterns around the world. Robot submarines opened entirely new possibilities for ocean exploration by removing the safety constraints that limited human diving operations. These unmanned vehicles could operate for months in environments too dangerous or remote for manned submersibles, providing continuous observations of deep-sea processes. Early remotely operated vehicles were tethered to surface ships by cables that limited their range and maneuverability. But as technology advanced, autonomous underwater vehicles began operating independently, following pre-programmed missions that could take them hundreds of kilometers from their launch points. These robotic explorers revolutionized the study of hydrothermal vents by providing the first detailed observations of vent communities over extended time periods. Previous manned dives could only observe vent sites for a few hours, but robot submarines could monitor them continuously, revealing daily and seasonal changes in vent activity and biological communities. High-definition cameras mounted on these vehicles brought the deep ocean into sharp focus for the first time. Earlier underwater photography had been limited by poor lighting and water clarity, but modern systems could illuminate deep-sea environments with daylight intensity while recording in ultra-high resolution. The creatures revealed by these advanced cameras defied every expectation about deep-sea life. Instead of the sparse, primitive communities that scientists expected in the abyss, they found ecosystems as complex and diverse as tropical rainforests. Coral gardens flourished in the deep ocean, supporting communities of fish, crustaceans, and other creatures found nowhere else on Earth. Bioluminescent displays captured by these cameras revealed communication networks operating throughout the deep ocean. Creatures that had never been observed alive showed elaborate patterns of flashing lights, suggesting sophisticated behavioral interactions in environments scientists had assumed were too harsh for complex social behavior. Hydrophone networks deployed throughout ocean basins began eavesdropping on the acoustic environment of the sea. These underwater microphones revealed that the ocean was filled with sounds, whale songs traveling thousands of kilometers, the rumbles of underwater earthquakes, the crackling of ice sheets, and mysterious sounds that science could not yet explain. The famous bloop, an ultra-low frequency sound detected by Pacific hydrophones in 1997, generated intense speculation about unknown deep-sea creatures before being traced to the storm movement of Antarctic ice. But many other oceanic sounds remain unexplained, suggesting that the deep ocean still harbors phenomena beyond our current understanding. Whale song research benefited enormously from hydrophone technology. Scientists discovered that different whale species use distinct frequency ranges, allowing multiple conversations to occur simultaneously without interference. Blue whale calls at frequencies below human hearing could travel across entire ocean basins, creating communication networks of unprecedented scale. Deep-sea drilling operations began extracting sediment cores that preserved millions of years of ocean history in layers of accumulated particles. These cores contained microscopic shells, pollen grains, and chemical signatures that recorded past climate conditions with remarkable precision. Ice age cycles, changes in ocean circulation, massive volcanic eruptions, and even asteroid impacts left distinctive signatures in deep-sea sediments. By analyzing core samples from around the world, scientists began reconstructing the ocean's history over geological timescales and understanding how marine systems had responded to past climate changes. Computer modeling emerged as a crucial tool for understanding ocean processes that operated over scales too large or time periods too long for direct observation. Ocean circulation models could simulate the movement of water masses over decades or centuries, revealing how changes in one region might influence conditions thousands of kilometers away. These models also began predicting how ocean systems might respond to future climate changes. Simulations suggested that warming temperatures could alter current patterns, change the timing of seasonal processes, and shift the distribution of marine life in ways that would affect human societies worldwide. The integration of satellite data, computer models, and robotic observations created the first truly global picture of ocean dynamics. Scientists could now track individual water masses as they moved through the world's seas, monitor the seasonal cycles of plankton blooms, and observe how marine ecosystems responded to changing environmental conditions. Weather prediction improved dramatically as meteorologists began incorporating ocean temperature data into their forecasts. The thermal mass of the ocean influenced atmospheric conditions over much longer timescales than terrestrial features, making sea surface temperatures crucial for predicting seasonal weather patterns. Hurricane intensity forecasting advanced significantly when scientists learned to monitor ocean heat content along storm tracks. Hurricanes derive their energy from warm ocean water, so storms passing over areas of high heat content tend to intensify, while those encountering cooler water weaken. As this chapter concludes, technology has transformed our understanding of the ocean from a mysterious void to a complex, dynamic system operating according to physical principles we can measure and predict. The invisible ocean has become visible through instruments that reveal processes occurring from the surface to the deepest trenches. These technological windows have shown us that the ocean contains phenomena operating on every scale imaginable, from microscopic plankton migrations to current systems that span ocean basins. But they've also revealed that vast mysteries remain hidden in the depths, waiting for the next generation of explorers and instruments. The next chapter will explore the questions that keep modern ocean scientists awake at night, the mysteries that our most advanced technology has revealed but not yet solved. Part 6. Mysteries Still Hidden in the Deep. Despite all our technological advances, sophisticated instruments, and decades of systematic exploration, an uncomfortable truth confronts anyone who studies the ocean. We have explored less than 5% of this vast underwater realm. The remaining 95% harbors secrets that make the surface of Mars seem familiar by comparison. In our own planet's depths, mysteries persist that challenge our understanding of life, geology, and the physical processes that shape our world. The numbers alone should give us pause. We have better maps of the moon's surface than we do of our own ocean floor. Our most detailed seafloor maps still contain blank areas larger than entire continents. When oceanographers plot the known locations of hydrothermal vents, seamounts, or deep-sea coral gardens, vast gaps remain where similar features almost certainly exist, but have never been detected. Here's what makes the unknown ocean so intriguing. Every new exploration reveals phenomena that don't fit existing scientific models. The deep scattering layer, that mysterious zone of marine life that migrates vertically each day, contains biomass that could exceed all fish caught by humanity combined. Yet we can barely identify the creatures that compose this massive biological phenomenon, let alone understand how such enormous populations sustain themselves in the deep ocean. Recent sonar surveys have detected what appear to be coordinated movements within the deep scattering layer, Norton, organized patterns that suggest communication or collective behavior among billions of individual organisms. These patterns operate over scales of hundreds of kilometers and seem to respond to seasonal changes, lunar cycles, and other environmental cues in ways that science cannot yet explain. The mystery deepens when we consider the energy requirements for supporting such massive populations in the deep ocean. Traditional food webs suggest that deep-sea life should be sparse, limited by the small amount of organic matter that filters down from surface waters. Yet the deep scattering layer implies the existence of highly productive ecosystems operating according to principles we don't fully understand. Turbidity currents represent another category of ocean mystery that keeps sedimentologists awake at night. These underwater avalanches can move billions of tons of sediment across ocean basins at speeds exceeding 100 kilometers per hour, yet predicting when and where they occur remains nearly impossible. Most turbidity currents are detected only after they happen, when their deposits are discovered on the seafloor or when they damage underwater cables. The triggers for these massive underwater landslides seem almost random. Some occur during earthquakes, others during storms, and many happen during periods of apparent calm when no obvious triggering mechanism exists. The inability to predict turbidity currents poses serious challenges for underwater infrastructure, deep-sea mining operations, and scientific equipment deployments. Recent discoveries suggest that turbidity currents may be far more common than previously thought. Sediment cores from around the world contain evidence of massive underwater avalanches that occurred throughout geological history, including some that transported sediment loads exceeding the annual discharge of all terrestrial rivers combined. These ancient flows reshaped entire ocean basins in ways that current models cannot fully explain. The ocean's role in carbon cycling presents perhaps the most urgent mystery facing climate scientists. The sea absorbs approximately 30% of all carbon dioxide produced by human activities, yet the ultimate fate of this carbon remains largely unknown. Some dissolved carbon dioxide reacts with seawater to form carbonic acid, gradually acidifying the ocean. Some is incorporated into marine organisms and eventually settles to the seafloor, but significant amounts seem to simply disappear from measurable reservoirs. This missing carbon represents one of the largest gaps in our understanding of Earth's climate system. Without knowing where the carbon goes or how long it remains sequestered, scientists struggle to predict how much additional carbon dioxide the ocean can absorb before reaching saturation. The ocean's carbon storage capacity could influence the rate of atmospheric carbon dioxide increase and the severity of future climate changes. Recent research has revealed that deep-sea sediments contain vast stores of carbon in forms that don't fit conventional models. Methane hydrates, crystalline structures where methane molecules are trapped in cages of water, ice, occur in seafloor sediments around the world in quantities that exceed all known fossil fuel reserves. These deposits remain stable under the high pressure and low temperature conditions of the deep ocean, but could potentially release enormous amounts of greenhouse gases if those conditions change. The acoustic environment of the deep ocean harbors mysteries that challenge our understanding of marine communication and behavior. Hydrophone networks detect sounds that travel across entire ocean basins but cannot be attributed to any known source. The famous bloop sound recorded in the Pacific was eventually traced to ice movement in Antarctica, but many other oceanic sounds remain unexplained. Ultra-low frequency calls detected by underwater microphones suggest that some form of long-distance acoustic communication operates in the deep ocean. These sounds, with frequencies so low that they travel thousands of kilometers with minimal attenuation, could theoretically allow creatures to maintain contact across vast distances. But identifying the sources of these calls and understanding their purpose remains one of marine biology's greatest challenges. Some research suggests that these ultra-low frequency sounds might represent a form of biological sonar used by large marine animals to navigate or locate prey across ocean basins. Whales are known to use echolocation for navigation and feeding, but the possibility that they might use even lower frequencies for continent-scale communication opens entirely new questions about marine animal behavior and intelligence. Seamounts, underwater mountains that rise from the ocean floor without breaking the surface, represent biological mysteries on a massive scale. These isolated underwater peaks support endemic species found nowhere else on Earth, yet the mechanisms that allow such diversity to develop and persist in isolation remain poorly understood. Each seamount seems to harbor unique assemblages of corals, fish, and invertebrates that have evolved separately from populations on nearby underwater mountains. The degree of endemism suggests that seamounts have remained isolated for millions of years, despite being connected by continuous water masses. How species colonize seamounts initially, and why they subsequently develop into unique communities, challenges conventional understanding of marine biogeography. Recent surveys have revealed that seamounts are far more numerous than previously thought. New mapping techniques detect underwater mountains at an average rate of several per day, suggesting that the total number of seamounts might exceed 100,000. If each seamount supports unique biological communities, the total diversity of deep-sea life could far exceed current estimates. Deep-sea mining operations beginning to extract minerals from seamounts and abyssal plains threaten to destroy these ecosystems before science can study them. The slow growth rates of deep-sea organisms mean that ecosystems damaged by mining might require centuries or millennia to recover, if they can recover at all. The connection between ocean circulation and rapid climate change represents perhaps the most critical mystery for understanding Earth's future. The Atlantic meridional overturning circulation, which includes the Gulf Stream, shows signs of slowing down, possibly due to freshwater input from melting Arctic ice. This circulation system has remained relatively stable for thousands of years, but paleoclimate evidence suggests it can shut down completely during periods of rapid climate change. If this circulation system were to collapse, the consequences would extend far beyond ocean science. Europe's climate would become much colder. Tropical rainfall patterns would shift dramatically, and sea levels would rise along the eastern coast of North America. Yet current models struggle to predict whether such changes are decades away or already beginning. Ice core records from Greenland show that past collapses of Atlantic circulation occurred within decades rather than centuries, suggesting that the ocean system can reach tipping points beyond which changes accelerate rapidly. Identifying these tipping points and their early warning signs represents one of the most urgent challenges in climate science. The discovery of extensive life in ocean sediments has revealed another realm of biological mystery. Microorganisms live hundreds of meters below the seafloor in sediment layers that haven't been exposed to surface conditions for millions of years. These deep biosphere communities exist at the limits of life, surviving on minimal energy sources and reproducing extremely slowly. The biomass of these deep sediment communities may rival that of all surface life on Earth, yet their role in global biogeochemical cycles remains largely unknown. Some of these organisms appear to be metabolically active, despite existing in environments with virtually no available energy, challenging fundamental assumptions about the requirements for life. Recent drilling operations have discovered microbial communities at depths exceeding 4 kilometers below the seafloor, suggesting that life extends much deeper into Earth's crust than previously thought. These extreme environments might provide analogues for life that could exist in the subsurface of other planets or moons throughout the solar system. Strange phenomena continue to emerge from deep ocean exploration that don't fit existing scientific frameworks. Brine pools on the seafloor create underwater lakes where dense salty water flows like rivers beneath normal seawater. These underwater water bodies support unique biological communities and create three-dimensional habitat structures in the deep ocean. Glass sponge reefs in the deep Pacific create underwater forests of silica structures that can persist for thousands of years, building complex three-dimensional habitats that support diverse communities of fish and invertebrates. The mechanism by which these glass sponges coordinate their growth to create reef-like structures remains mysterious. Underwater waterfalls, where dense water cascades off continental shelves into abyssal depths, create physical and chemical gradients that influence the distribution of deep-sea life. These underwater cataracts transport nutrients, oxygen, and sometimes living organisms from shallow to deep environments, but their ecological impacts are poorly understood. The ocean's magnetic properties reveal another layer of mystery. The seafloor preserves a record of Earth's magnetic field reversals in volcanic rocks, but some oceanic magnetic anomalies don't match any known geological processes. These magnetic signatures might indicate previously unknown types of seafloor volcanism or the presence of unusual mineral deposits. As this chapter of Oceanic Mysteries concludes, it becomes clear that our most advanced technology has revealed not just what we know about the ocean, but the vastness of what we don't know. Each new discovery seems to raise more questions than it answers, expanding the boundaries of mystery rather than shrinking them. The deep ocean contains phenomena operating on scales from microscopic to planetary, over time periods from seconds to geological epochs. Understanding these systems requires not just better technology, but new theoretical frameworks that can encompass the complexity of oceanic processes. The next chapter will explore how humanity is preparing to tackle these mysteries, developing new technologies and approaches that might finally unlock the secrets hidden in the deepest parts of our blue planet. The future of ocean exploration is arriving not in decades, but in years. Autonomous underwater vehicles no longer require constant supervision from surface ships, the marmots. They roam the depths for months at a time, following programmed missions that take them thousands of kilometers from their launch points. These robotic explorers send discoveries back to shore through fiber optic cables that span entire ocean basins, creating a real-time connection between the deepest trenches and research laboratories on the surface. Here's what's actually happening as ocean technology evolves. Artificial intelligence systems analyze incoming data streams from underwater sensors, identifying patterns and anomalies that would take human scientists months to detect. When an autonomous vehicle encounters something unexpected, timed a new species, an unusual geological formation, or a previously unknown hydrothermal vent, IA, the AI can recognize its significance and redirect the mission to investigate further. These intelligent systems operate continuously, processing information 24 hours a day without fatigue or distraction. They can monitor multiple data streams simultaneously, tracking water temperature, chemical composition, biological activity, and geological processes, while maintaining precise navigation in the crushing depths where GPS signals cannot penetrate. The engineering challenges of deep ocean exploration are driving innovations that push the boundaries of materials science and robotics. Pressure housings must withstand forces that would crush conventional submarines like aluminum cans, while maintaining precision control over delicate scientific instruments. New materials inspired by the shells of deep-sea creatures are being developed to create lighter, stronger components for underwater vehicles. Bio-inspired design is revolutionizing underwater propulsion systems. Engineers study how fish and marine mammals move through water with such efficiency, then apply those principles to create vehicles that can operate for extended periods on limited battery power. Some experimental designs mimic the undulating motion of eels or the jet propulsion of squid, achieving levels of efficiency impossible with conventional propellers. The search for life on Europa and Enceladus, moons of Jupiter and Saturn that harbor subsurface oceans beneath their icy shells, is driving the development of technologies that will revolutionize Earth's ocean exploration. NASA and other space agencies are designing autonomous submarines capable of operating in alien seas, completely cut off from Earth-based control due to the vast distances involved. These space-bound underwater vehicles must possess unprecedented autonomy, capable of making complex decisions about where to explore and what to investigate without any input from human controllers. The artificial intelligence systems being developed for these missions will far exceed anything currently deployed in Earth's oceans, creating capabilities that will eventually enhance terrestrial ocean research. The technologies developed for exploring alien oceans will return to Earth as advanced systems capable of exploring our most remote and dangerous underwater environments. Ice-covered seas, deep ocean trenches, and underwater caves that currently challenge human explorers will become accessible to robotic systems designed for the ultimate in autonomous operation. Advanced submersibles are approaching the engineering capabilities needed for permanent underwater habitats, where humans could live and work beneath the waves for extended periods. These underwater cities wouldn't just be research stations, they could become self-sustaining communities that harvest energy from ocean currents, grow food using marine aquaculture, and manufacture needed materials from seawater minerals. The concept of underwater cities is transitioning from science fiction to engineering possibility. Advances in closed-loop life support systems, underwater construction techniques, and pressure-resistant architecture are making it feasible to create permanent human settlements on the ocean floor. These communities could serve as bases for deep-sea research, mining operations, and marine conservation efforts. Underwater cities would offer unique advantages for certain types of research and industry. The stable temperature and pressure conditions of the deep ocean could benefit manufacturing processes that require precise environmental control. The isolation from surface weather and the abundance of space could make underwater settlements ideal for certain types of scientific research or technological development. Marine protected areas are expanding toward the goal of protecting 30% of ocean area by 2030, creating underwater wilderness preserves larger than entire continents. These vast marine reserves will serve as natural laboratories where ocean ecosystems can function without human interference, providing baseline data for understanding how marine systems respond to changing environmental conditions. The implementation of such large-scale marine protection requires new technologies for monitoring and enforcement. Satellite surveillance systems can track fishing vessels in real time, while underwater sensor networks detect unauthorized activities in protected areas. Artificial intelligence systems analyze patterns of human activity to predict and prevent illegal fishing or other violations of marine reserves. These protected areas will also serve as refuges, where marine species can recover from overfishing and other human impacts. Early results from existing marine reserves show that fish populations can recover dramatically when given protection, often supporting spillover effects that benefit fisheries in surrounding areas. Laboratory experiments investigating ocean acidification and temperature changes are revealing how marine ecosystems might adapt to rapidly changing conditions. Some organisms show remarkable resilience, adjusting their physiology or behavior to cope with environmental changes that would have been lethal to previous generations. Others face extinction if current trends continue. These controlled experiments provide crucial data for predicting how ocean ecosystems will respond to future climate changes. By subjecting marine organisms to projected future conditions, scientists can identify which species are most vulnerable and which ecological relationships are most likely to be disrupted. The results of these experiments are being incorporated into computer models that simulate ecosystem responses to various climate scenarios. These models help identify potential tipping points where small additional changes could trigger large-scale ecosystem collapses, providing early warning systems for marine conservation efforts. The discovery of extremophile organisms in Earth's deepest trenches is providing blueprints for life that could survive in alien oceans throughout the galaxy. These creatures thrive under conditions of crushing pressure, extreme temperature, and toxic chemistry that would instantly kill most life forms. Understanding how they survive such conditions expands our concept of where life might exist in the universe. Some extremophiles derive energy from chemical reactions that occur in environments completely isolated from sunlight. Others can survive temperature extremes that exceed the normal limits of biological chemistry. These discoveries suggest that life might be far more common in the universe than previously thought, existing in environments that were once considered completely hostile to biological processes. The study of extremophiles also provides insights into the early evolution of life on Earth and the conditions under which life first emerged. Many extremophile biochemical pathways appear to be very ancient, possibly preserving metabolic strategies that evolved in Earth's earliest oceans. Artificial intelligence is beginning to analyze patterns in ocean data streams that human scientists could never process manually. These systems can identify subtle correlations between ocean temperature, chemistry, biology, and climate that operate over scales of time and space too large for human comprehension. The insights emerging from these analyses are revealing previously unknown connections between ocean processes and global environmental systems. Machine learning algorithms can process satellite data, sensor readings, and biological observations simultaneously, identifying patterns that predict everything from hurricane intensification to fish population crashes. These predictive capabilities are becoming essential tools for weather forecasting, fisheries management, and marine conservation planning. AI systems are also being trained to recognize new species and biological phenomena in underwater video footage. As the volume of data from underwater cameras increases exponentially, human scientists cannot possibly review all the footage manually. Artificial intelligence can scan thousands of hours of video, flagging unusual organisms or behaviors for human review. Climate prediction models are incorporating increasingly sophisticated representations of ocean processes as scientists recognize the crucial role of marine systems in global climate regulation. The ocean's capacity to absorb heat and carbon dioxide directly influences the rate and severity of climate change, making accurate ocean modeling essential for climate predictions. These models are revealing that small changes in ocean circulation patterns could trigger rapid shifts in global climate, similar to the sudden climate changes that occurred during past ice ages. Understanding these ocean-driven climate mechanisms is becoming crucial for predicting and preparing for future climate changes. Ocean-atmosphere interaction models are also improving weather prediction on seasonal to annual timescales. By accurately modeling how the ocean stores and releases heat, meteorologists can provide better forecasts of phenomena like El Niño, which influences weather patterns around the world. Understanding ocean systems is becoming humanity's key to developing sustainable ways to feed 10 billion people from marine resources. Aquaculture operations are expanding from coastal waters into the open ocean, where they can operate on scales necessary to make significant contributions to global food security. These offshore aquaculture systems must work in harmony with natural ocean processes, using currents for water circulation and nutrient transport, while minimizing impacts on wild marine ecosystems. Advances in marine biology and engineering are making it possible to farm fish, shellfish, and seaweed in open ocean environments, while maintaining ecological sustainability. The development of sustainable marine fisheries depends on accurate understanding of fish population dynamics and ecosystem relationships. New monitoring technologies can track individual fish throughout their life cycles, providing data on migration patterns, breeding success, and population health that enables more precise fisheries management. Ocean exploration is approaching a technological threshold where the deep sea will become as accessible as the surface waters are today. Advances in materials science, robotics, and artificial intelligence are creating capabilities that will finally allow systematic exploration of the vast underwater territories that remain unknown. This comprehensive exploration will likely reveal biological and geological phenomena that challenge our current understanding of how Earth systems work. The discovery of new forms of life, previously unknown geological processes, and unexpected connections between ocean and climate systems will provide the scientific foundation for managing our planet's future. The technologies being developed for ocean exploration will also enhance our ability to predict and respond to environmental changes. Real-time monitoring of ocean conditions will provide early warning of hurricanes, tsunamis, and other natural disasters, while detailed understanding of marine ecosystems will guide conservation efforts. As human activities increasingly affect ocean systems, the need for comprehensive ocean science becomes more urgent. Climate change, pollution, and overfishing are altering marine environments at unprecedented rates, requiring scientific understanding that can keep pace with the speed of change. The future of ocean science lies not just in discovering what exists in the sea, but in understanding how ocean systems respond to human activities and how we can modify our behavior to maintain healthy marine environments. This understanding will be crucial for ensuring that future generations inherit oceans as productive and diverse as those we know today. The call of the ocean continues to beckon, not just to explorers seeking adventure, but to scientists, engineers, and policymakers working to understand and protect the marine systems that sustain all life on Earth. The next chapter in ocean exploration will be written by those who answer this call, using the tools of modern science to unlock secrets hidden since the beginning of time. In the depths of our blue planet, discoveries await that will transform our understanding of life, climate, and the intricate systems that make Earth habitable. The ocean's future is calling, and humanity's response will determine not just what we learn about the sea, but how well we learn to live in harmony with the waters that cover our world.